Hi, everyone. I'm Kamelia, and I'm from the data science team on Etsy. So today I'm going to talk to you about search ranking and learning to rank. So I'm going to talk to you about a little bit of my background, and then I'll share my slides, and we'll get the talk started. Awesome, cool. So I was just going to make sure. Hi. Cool. Awesome. So I work as part of the search sciences team in Etsy, and over the years, I've worked on many different machine learning problems, starting from recommendations and personalization, where we have different modules and we come up with personalized recommendations for the users, be it in the emails or on the homepage of our website. And recently, I've been working more on search ranking, so the algorithms that go into search and how we basically rank the items that are relevant for different queries on the website, and a little bit of advertisement, basically click-through rate prediction, and running an auction and what kind of things we can optimize to run basically a generalized second price auction. So I'm going to share my slides. Cool. Hopefully you can see them in full screen. So basically, I'm going to talk about learning to rank in e-commerce. Like I mentioned, I'm part of the search sciences team at Etsy. And before joining Etsy, which was 4 years ago, I was doing a PhD in machine learning in Drexel University. All right, so let's get started. I realize that not everyone is familiar with Etsy, so I'm just going to give you a background of what Etsy is and what do we do on the website. So basically, Etsy is a global marketplace where people around the world connect both online and offline to make, sell, and buy unique goods. So Etsy is a peer-to-peer market. So basically, we have sellers, and then we have a group of buyers, and they run a business peer-to-peer. And by no means it's mutually exclusive. So we have wonderful sellers who are also buyers and buyers who are also sellers. So as of December 2015, we have 1.6 million active sellers, 24 million active buyers, and more than 35 million items for sale, which on Etsy, we call them listings. And I will show you an example later on. So like I said, we have 24 million buyers, and 92% of them agree that Etsy offers products that they cannot find elsewhere. And that's interesting because it produces a lot of unique challenges for us. A lot of places, especially in e-commerce, we have barcodes. So the problem of recommendations, finding personalized items, or just ranking in terms of search becomes a little bit easier because you have a lot of items that are basically the same and they have barcodes. But that's not the case for Etsy. Individual items are pretty unique. So it becomes more and more important to find different items that match users' taste or how to retrieve them for special queries. So this is a storefront in Etsy, which we call it the shop homepage. As you can see on the top, we have a shop banner, and then we have a bunch of listings for sale. Each one of those items on the below is basically a listing for sale. And this is a view from the listing, and it's important because I'm going to talk later on about the features that we extract at listing level. So let's take a look at it. Basically, a listing on Etsy has a set of images, and we have title, and then we have tags, we have descriptions, we have ratings, we have price, and so on and so forth. So there's a lot of information in Etsy listings that we can use for ranking in e-commerce. So this is the view of Etsy search page. So given a query, for example, a crochet blanket here, the problem of learning to rank is essentially finding the listings or the items that are most relevant to the query. So as you can see, for this specific query, crochet blanket, we have so many results. It's more than 67K actually results. So that's a lot of results. So the problem here becomes, how do we rank them so they're most relevant to the query and the users are gonna interact with them more, basically click on them, favorite them, purchase them, and so on and so forth. So that's a problem I'm going to talk about today. It's called learning to rank. And basically, it's given a query and a set of documents. How do we retrieve the top queries that match that document, and what's the ranking that we come up with? So historically, people, the way that they solved the ranking problem is basically not a machine learning approach. It's basically you have a set of documents and you do a heuristic-based approach of those documents with your query and see which one of them basically matches the text of the query, and then retrieve them based on that score. But there is a lot of machine learning approaches, and this is a well-studied problem in industry. So the three basic approaches that we have in learning to rank is pointwise, pairwise, and listwise. So I'm going to talk about all of them briefly, but the one that we're going to mostly focus on today is pairwise ranking. So basically, the pointwise learning to rank is where you come up with a score, a relevance score, that basically a similarity score between your query and your document. And the way that you can come up with is that you basically extract some sort of features, a feature vector from your item, and then you do a classification and see that if that item is basically relevant to the query or not. The pairwise ranking basically is viewing the problem more of a regression base. So basically you find the difference between the relevance of two neighboring documents relative to a query. So basically, given a query, you come up with pairs of documents where one of them is clicked, the other one is not clicked, and then you basically featureize the difference between these two and do a regression on it, or a classification, and come up with a relevance score. And then eventually the listwise basically assumes that the input is an entire set of documents associated with a query, and then the output is a ranked list, and then basically minimizes the loss of the distance of ranking generated by the model to the perfect ranking for the set of documents. So like I said, we're going to focus on pairwise ranking, and I'm going to talk about it in details. But basically, one of the things to notice is that while a pointwise approach might be simpler to think of in terms of a classification, it has a lot of problems. So basically, if you can think about it, the queries who have a large set of documents are going to dominate your loss function, a global loss function. So basically, that's one of the motivations that we do pairwise ranking. So I'm going to cover the basic algorithmic approach to pairwise ranking using only text information. And then in the next section, I'll show you how we mix it with image features that are transfer learned from a deep neural network, and we do multimodal pairwise ranking. Okay, so pairwise learning. In pairwise learning, basically, we assume each training instance represents a pair of items from same set of search results in your log. So basically, assume that you have a given query, you mine the logs from the search, and then you find items that are next to each other, and one of them is clicked and one of them is not clicked. So the goal of our learner is basically to learn to order item 1 and item 2 correctly with respect to user preference decision that's found in your logs. So that's all you care about. So given a query and 2 items, what's the correct way of ranking only these 2 documents? And then obviously we'll extend it to all the items that we have in our listing. So before we talk about it a little bit more in terms of the ranking algorithm, basically I want to talk about the features a little bit. So these are 2 listings that are retrieved for a query wolf, for example. So the features that are used for these listing representation basically is just the tags. So as you can see, both of them have the tag wolf, basically. And so that's why we're retrieving them. So feature representation and how essentially you're going to encode your listing into one feature vector is really important. That's the point I want to emphasize. But for simplicity, assume for now, we just have tags as our features. So basically each item that we have for sale is just a set of text tokens that are the tags of the listing. And those are the listings, for example, that are retrieved for a query wolf based on that feature representation. We'll see later on why using images can help kind of detangle these difficult cases. Okay, so with that assumption that we only represent each listing with each set of tags, this is how we create labels for pairwise features. So assume, again, we have a query, housewarming gift, and then we have two listings. One of them, the listing on my left, is clicked on, and the listing on the right is not clicked on. So if you think about it, basically we can assign, we will assign the label as the listing that's clicked on minus the features of the listing that's not clicked on, and then we assign a positive one to it. So if the listing that's clicked on is presented first, we assign a label +1, and if the listing that's not clicked on is represented first, then we assign a label -1. So let's take a look at the example. So basically, in the first instance, you're seeing a label creation of the label +1. So basically, the feature representation of listing that's clicked is housewarming gift photo, and we minus it with the feature representation of the listing that's not clicked on, which is housewarming gift ceramic tile, and then we assign a label +1 to it. So now we can obviously reverse this and put the listing that's not clicked on first, and then we have the feature representation of that listing, housewarming gift ceramic tile, and then we put the second listing, which is clicked on, as the second feature representation, which is housewarming gift photo, and then we assign a label -1, which basically shows that the ordering here is wrong and the ordering for the +1 label is correct. So then how would you make sure that basically your label creation is fair, or you have balanced data set? Basically, you have enough samples of both the positive and the negative class. Basically, we flip a coin each time, and based on that, if it's greater than, if it's heads, basically we'll form a +1 instance, and if it's tails, we'll form a -1 instance. So that's how we create the labels, and we make sure the data set is balanced. Okay, so now that we have a set of different labels created from our listings and from historical search logs, we can just simply transfer the problem into a classification problem with SVM. So basically your goal here becomes that you can predict based on the listing representation, is that ordering correct or it's not correct? Is that for the test instances, is the label +1 or -1, and then you have your ranking basically. So the production pipeline, or the one that we use right now, looks like this. So basically, from the historical search logs, we mine item pairs, we create the feature vectors. There's a step missing there that's basically feature representation, but essentially we encode all the listings in terms of that tags that I showed you, and then we come up with the difference of the vectors, which basically was the clicked minus the not clicked, or not clicked minus the clicked, and we assign the labels to them, and then we feed them into a SVM trainer, and we come up with a model. So now the model is deployed in production, and in production time, we have different items, and we have their feature vector representation. So we just apply the model in a ranking pass and get a ranking that's basically shown on the search page. So that's all good, and it looks good, and it works pretty well in most industry places. But we have a set of problems that are unique to our own marketplace, and that's the problem of, for example, tag stuffing. So not always the text representation of a listing is accurate. So like the example that I showed you, we can have listings that are basically not a wedding dress, but we sellers tag them with wedding dress because that's a good query, and it's basically has a lot of traffic. So you can see, like, here is 3 examples of not a wedding dress for sure, but it's tagged with wedding dress. So now if you were to use the feature vector that we talked about, which is basically the tag representation of the listing, you would retrieve all of these 3 as a highly ranked listing for a query wedding dress. But that wouldn't be accurate. So I'm going to talk about an extension of Learning to Rank to actually incorporate image features, or get the complementary information that exists in the image to verify these tags and make sure that the listing they're actually showing for each query is in fact a wedding dress, for example. So the idea here is, let's again take a look at the listing. So as you can see, like we said, we have a set of images that represent the listings, and we have the title, the tag, and so on and so forth. So in most cases, we extract only text features like unigram, bigrams, trigrams of the title or the description, and the tags. And like I mentioned, these can be inaccurate. So the idea here is that we're going to use the listing image 2 as a feature vector and represent the image as a set of numbers and make sure that that actually is going to contribute to the ranking algorithm. So let's talk about image features a little bit and see what I mean when I say image features. So historically, there have been many different image features. People have played around for many years with low-level features, be it like the color, the texture features, and more recent than that, SIFT features, HOG, text fonts, and so on and so forth. And recently, there have been a lot of work on deep learning and using different networks to come up with different features that basically represent an image. So here we used a deep learning approach to come up with the image features that basically or for our listings. So we use a pre-trained network because it's easier for us to basically transfer learn the features rather than training our own network. So I use a pre-trained VGGnet on ImageNet to basically transfer learn image features from our listing features. So a VGGnet basically is an 18-layer convolutional neural network, and basically the idea here is that the network is trained on ImageNet to do classification on those tags that you see. And as you can see, for example, the last layer there, which is basically the classification score, tells you if the input image is car, truck, airplane, ship, horse, and so on and so forth. And the input to the network is basically RGB vector representation of the image that you have. So basically, the transfer learning happens when with a pre-trained network is when we basically feed in our query image, which is not from the network that's trained on, and then we basically remove the scores, the last layer, and then we take that the last layer basically as the representation of the image. So the idea here is that since the network is trained on a large set of images, basically it has a good understanding. The lower the levels, the more low level the features are, and the more you go deeper in the network, basically the features become more semantically meaningful. So for our case, basically, like I said, we have a pre-trained VGG network from ImageNet, and we feed our own images to the network, and then we take the last fully connected layer as the feature representation for that specific image. Okay, so remember that I mentioned that Etsy items or listings basically have a set of text description and tags, and then they have images. So we have both modalities. We have the text modality, and then we have the image modality. So what we do is essentially just feed in the whole listing into our multimodal embedder, basically, which is essentially just extracting the image vector and then extracting a text vector, and then basically concatenate them together as one single multimodal vector representation of the listing. So there are fancier ways, of course, of adding the features together, or like learn a network that's trained at the same time on both modalities instead of just concatenate them. But in this paper, we only basically focus on the concatenation because it was the easiest one to implement. Okay, so let's go back to the learning to rank problem. So remember that our goal was to basically retrieve items that are most relevant to the query. So let's look at that query, mid-century desk, and then we can see that we have a set of listings that are retrieved, and then the user clicks on one of them. So basically, this is the historical search logs, and I'm going to talk about the instance creation. So we have basically a set of click listings and a set of ignored listings. We feed both of them to this multimodal embedder, essentially, and we extract the multimodal feature vector for all of the click listings for each query and all of the ignored listings for each query. So basically, that's the feature representation now, which is multimodal, and it also takes advantage of the images. Okay, so again, similar to what we had before, we form these feature vectors and assign labels to them. So if the clicked multimodal feature vector is first, minus the ignored one, we assign a label +1. And if it's the ignored multimodal feature vector minus the clicked one, we assign a label -1. And now we have the representation, and the rest of the algorithm stays the same. So let's look at some of the results in a real world scenario. So this is the comparison of basically the text-only ranking for a query bar necklace to the multimodal ranking for that query bar necklace. So if you look at the results, even the first one, the 90th percentile, the first row, you can see that for the text-only model, we see a lot of listings that are really not bar necklaces. Not even the first one, which is like buy any 2 items, and the third one for $1, and it's a heart necklace. But if you look at the same row in the multimodal ranking, you can see that it's an obvious improvement on the quality of the retrieved listings. So it's fair to say that the ranking in the multimodal sense is much better than the ranking on the text-only sense. And obviously, we do offline evaluations to make sure that the ranking is valid. We do NDCG, and we have seen that the multimodal ranking significantly improves the ranking quality as compared to the text-only ranking. This is another example. This time the query is cross necklace. So again, if you see on the first row, we see some lower quality listings, and the same row on the multimodal ranking is of higher quality. So overall, it's interesting to see that the results are actually much better in the multimodal case, and most of them actually do have a cross on them versus on the text only. Some of them basically are not even the relevant query, and the image basically takes care of that. So it's pretty interesting. So let's go back to our favorite query, the wolf. Before, with the text only, we were retrieving this first listing, which is like a shirt, I guess, which doesn't have any wolf in it, but it's tagged with a query wolf. And then we were ranking that higher than the listing on the right. But using the multimodal embedder, the listing on the right gets ranked much, much higher because it actually does have a wolf on it. And this is the same idea. Again, previously we were ranking this accessory higher for a query leather bag, and the listing on the right was ranked much lower. But using the multimodal ranking, the item on the right gets ranked much higher than the item on the left. Another example, this is for a query wedding band. So the earrings on the left were being ranked much higher with a single modality text-only approach. And the wedding band on the right now gets ranked much higher using the multimodal embedder approach. Okay, so this is the idea, and you can read more about it in the paper that I have on there if you're interested in that kind of thing. But now I'm going to talk a little bit about our production pipeline and how we actually apply the model in our production system. So basically, like I mentioned, we collect tags from historical search logs. We have the information based on each query, what the users clicked on and what they ignored. So we form our pairwise instances by basically taking the adjacent listings and looking at if one of them is clicked and the other one is not clicked. And we form our training instances and basically pass it to the SVM, and we learn the ranking algorithm. So now the model can be applied in 2 ways. It can basically be trained in 2 ways, real-time and offline. So obviously, the benefits of the real-time is that it can handle unseen items. If the model is offline, basically we cannot handle unseen items, but there is no cost to feature complexity. So things like, for example, image features, which might be more expensive, it makes sense to train that model in an offline setting rather than real-time. But the cons basically is that in real-time, the complexity of query time feature computations goes higher, the latency becomes higher, versus in the offline setting, the cons is that the computations compound as considerations increase, basically. So this is what we have for the actual production pipeline. So basically, we have a storage for the model, and then when the user query comes in, we use Solr to retrieve the top K results, and then we apply a re-ranking pass, which basically applies the model and re-ranks the top K results, and that's what gets shown to the user. So one of the actual considerations when applying ranking models is how to gain confidence and how to make sure that when we are introducing a new ranking model, we're not changing things too much, or we don't have performance issues, and so on and so forth. So I would say the most important factors to watch out for is basically performance issues and understanding some sort of offline metric, basically similar to NDCG or something like that, and make sure that we understand the changes that we are making. So in Etsy, the way that we gain confidence is that we test both of them. So we have a tool that's called Tire, and we use it to do performance replays and ranking replays. So basically, the idea here is that we test the model or the changes on historical data, and we basically see how we are changing the production traffic. So this is essentially, for example, a performance test that's basically testing having different term boosts. It's just like one model that we try, and then we look at the results and see if there is any performance considerations or things like that. And then obviously we take a look at the latency, which is important to make sure that we are not making the search so slow that the users will basically just leave. And then obviously, like I mentioned, we have ranking replays where we take a look at the difference between the control and the variant that we are basically A/B testing with to make sure how much we are shifting things. This is an item level rank shift, which basically is telling you at the item level how much things are shifted around. And like I mentioned, we have offline evaluation too. So one of the well-known metrics for ranking is NDCG, and we basically compare the different variants and the control in terms of NDCG and make sure we understand if the variant has lower or higher, or what's the relative NDCG gain. And then at the end, we run basically a ranking test that shows us for different queries what items are dropped and what items are added. If we have more diversity in the control versus the variant, and what's the average price change. And these are all the things that are important to keep an eye for when you're doing ranking changes. And obviously we have explain box. So basically if we're not sure about the changes that has happened at each step, we'll go in and we'll look at exactly what kind of things are triggering this specific ranking for this query. So what's next for our ranking in the future is basically the model that we have in production right now, although we showed that the adding images is going to be better in terms of the quality of the ranking, there is a little bit of infrastructure challenges with that. So that's one of the things that we're going to hope to do in the future, as well as I personally want to train models that are basically trained on our own images rather than directly transfer learning without any fine-tuning from ImageNet. So these are some of the things that we're going to focus on in the future. And finally, if you are interested in this talk, and if you're interested in ranking, in search, in machine learning, data science, all the cool stuff, please feel free to apply. And we are hiring both for the search ranking engineering team and for the machine learning and recommendations engineer, which is the data science position in San Francisco and in Brooklyn. That's all I have. Thank you so much. And please let me know if you have any questions. So I am gonna read the questions from the top. So Gilbert asks, how do you retrieve the items to be used by the model? Basically, so you can classify as only once you have the list, you can do it. So basically, from my understanding, you're asking how do we retrieve the top items? Like I mentioned, we use Solr. So we retrieve the top, assume like how many numbers, and then we do a re-ranking pass applying the model on those features that we have already stored, and then we get a score. Basically, that's what we have. You're asking using Solar means that you're using TF-IDF, basically recall, but that can retrieve more false positive results. Yeah, so that's one of the limitations of the approach that we have. But basically, we have performance issues too, right? So we have to get the results as fast as we can, and that's why we'd rather keep the model as simple as possible and basically just re-rank the top whatever number. So you can't re-rank the whole thing each time a query is issued. So basically, that's one of the reasons that we retrieve a top set of relevant items to that query, like you mentioned, the TF-IDF, and then we apply the ranking pass. Have you thought of using different approaches? Yeah, there are many things that we have thought of actually using in production, but we haven't got around to do many of them. I definitely think at least using image features in production can be a big help for us. So the next question, is there a 50-50 concat between text and image vectors? So it's not actually 50-50. So the feature vector for the images is much larger. So it doesn't necessarily have to be 50-50. It doesn't matter. So as many features as we have to represent the text, we just concatenate that with the feature vector for the images. So that's not necessarily 50-50. Bruno is asking, does the multimodal ranking use the same tags as the text only? How do you prevent correct tags to impact the image classification? So yes, the tags that we use for the image plus text is the same as we use for the text only. So basically the idea here is that that's the main reason that we use historical logs, because the idea here is that if the users click on a listing, it is more relevant to the query. So basically, when you have the text-only model, it's like you're basically ignoring the image, and then when you have the multimodal, you basically are taking the image into account. Can you shed more light on the production challenges of multimodal ranking? So off the top of my head, one of the challenges is indexing image features. So in production, you have performance considerations. So you like to return the results to the user as fast as possible. So indexing the image features is a little bit difficult. It can be done, but we have just not got around to doing it yet. Any experiments with joint visual semantic embeddings versus simply concatenating the image text vectors? So we have done offline experiments with them, not a live A/B test, but basically the idea is that you can basically come up with one neural network that has like a last layer, and then you feed the image and the text at the same time, and you get one representation, versus the way that you're doing it, that gets a text representation and concatenates it with the image representation. And the results in the offline setting are actually better, but we haven't done a live A/B test with it yet. I think I answered Bruno's question. Don't the image features harm the diversity of the results? I worry all top results will look the same. That's a very good question. So basically, I don't think it actually impacts the diversity too much, but just for the we haven't done a live A/B test with it, but we have a diversification step under ranking pass. So we basically make sure that we are adding some sort of shop diversity also at the same time that we are doing the re-ranking pass. So I would say the image vectors will make the results more relevant, but it could actually impact the diversity too. That's a very good point. So Gilbert is adding, if I add rare words and image, what if I add rare words and image? That's the average of the category. If I add rare words and image, that's the. Are you saying, meaning the TF-IDF will recall it? So basically, you're saying if you have a listing that has rare words in it and the image, which is the average of the category, the TF-IDF will recall it, and the model based on the image and the text will rank it higher. So you're trying to come up with a listing that basically gets ranked higher. Yeah, technically it should, but I don't think it's something that we need to worry about. But yeah, from a theoretical perspective, it should. Yeah, it should rank higher. That's a very good point. And Razwan is asking, what are some of the drawbacks of multimodal learning? So basically, the multimodal learning can improve the ranking and obviously can perform better in an A/B test or offline NDCG. But one of the drawbacks, at least right now for us, is performance issues. So indexing, the bigger the feature vector essentially, and the bigger the model, the harder it gets to do things in real time. So that's one of the things that it's a little bit difficult, and it needs more kind of infrastructure support, I would say. Also, if you think about it, so if you had like real-time settings and then you add a new listing and all of a sudden you want to search it, you basically had to extract features from it. So essentially you had to extract image features on the fly too, which is pretty expensive. In generally, everything that deals with images is a lot more expensive than text only, and that's why historically a lot of ranking, even CTR prediction models have been focused on text only, because you can get so far with text that it might not always be beneficial to use images as well. Salem is asking, can't you use the output of your neural network to give feedback to sellers? That is very good. We can definitely do that for sure. We have, actually, I have another paper that talks about image quality, and that can be used as a feedback point for the sellers, but it's not yet a product that we do. But we can definitely use an image quality, or basically tell the sellers that, okay, these tags is not matching the image, but we don't have any product around it yet. So Gilbert is asking, how do you treat multiple images? Do you use only one per listing? So we have up to 5 images, I think, for the listing. And at some point, I did some experiment of concatenating the feature vectors from all of them, but that's too expensive. So right now, yes, we only extracted the main image, the first listing image, as the image representation. Yeah, so basically the first image that the seller uploads is the one that we call the primary image, and that's the one that we extract features from. Thank you so much for attending. It was a pleasure, and hopefully I'll see some of you in other conferences too. All right, bye.